Hello everyone, it's time for another video with Mr. Tom and STEM Kids in Space! Today we want to talk about orbits. Let's say this is the Earth. I want to orbit around. How do I do that? If you were on top here and had a ball, might be this type of ball, might be this type of ball, any sort of ball, and you would throw the ball as hard as you could. It would go a certain distance, but because of gravity and because of the resistance of the air, it would only go a certain distance. If you could throw it harder, it might go a little bit further. If you could throw it even harder, which means even faster, it might go even farther. And if you could throw it fast enough, that is hard enough, it would still be coming down towards the Earth, still falling, but it would be going so fast that it's falling would take it all the way around the Earth. Now, people say if you threw the ball hard enough and you waited long enough, it would go all the way around, pop, hit you in the head. Probably not actually in the head because you'd be throwing on this side or throwing on this side. It'd whiz right by you. And that's what a rocket has to do. The rocket has to go up. You can't just go up. Because if you're just going up, you're not going to rotate. You went straight up and then turn off your rocket engine. At some point, it would just fall straight back down. So your rocket's got to go up and turn. Now if you're out in space and you try turning, that takes a lot of energy to go from this direction to that direction. If you watch a rocket launch, you'll actually see it go up, but you also see it turn because it's using gravity and air to help it turn. It uses less energy to turn the rocket when it's closer to the Earth and in the air. So we got to go up and we've got to turn. And we talked in another video, you only have to go up 100 miles. But you got to go fast enough to be going 17,000 miles per hour. So most of your energy is really getting you up to 17,000 miles per hour. And some of your energy is to get you up 100 miles. So you need both. How would we experiment with this? Most of us just naturally can't throw a ball 17,000 miles an hour. And we can't throw the ball up 100 miles. But we can do a simpler activity, a simpler experiment that demonstrates some of those principles. So for this activity, you'll get someone to help you and some sort of measuring device, just relative measurements, or you can get some way to measure distance. Let's say we're going to go outside in the backyard or out in the playground. We're going to take a ball, any ball, and we're going to try to throw it horizontally from our body. We're not going to throw it as hard as we can because for a couple of reasons. One, we're going to be throwing the ball several different times, so we want to be consistent. But we're just going to try to throw it out horizontally. It's going to go out. It's going to hit the ground. We're going to measure how far that is. We can put a stick in the ground if we're in the yard or on the playground. We get some sort of ruler and measure how far that is, some sort of measuring tape. So we're going to take our ball next and we're going to throw it at about 20 degrees up. It doesn't have to be perfectly accurate. It might be 30 degrees, it might be 15, but we don't want flat. We going to throw it with the same force as we threw it before when it was horizontal. We're going to release it. The ball is going to do something, land on the ground because of resistance, because of gravity. We're going to mark where that is. We're going to know how far that went compared to when we threw it horizontally. Now we're going to throw it again, this time at 45 degrees, which is about halfway between horizontal and straight up. That's 45 degrees. Now let's do another throw at 60 degrees. So that's more than 45, less than straight up. Straight up's 90 degrees. So something like that. Try to throw it with the same force. And finally, we're gonna, with the same force, throw the ball straight up, 90 degrees. Throw it up, something's gonna happen. It's gonna fall down. It should land like right about where you are, because we just went straight up. Now, because we don't always throw exactly the same, if you want to have even more information, more data, each one of those, throw it 3 times. Horizontal 3 times, 20 degrees 3 times, 45 degrees 3 times, 60 degrees 3 times, 90 degrees 3 times. What you're going to find is that the ball goes different amounts. But when we are flying in our rocket, we actually need to be going horizontal, and we need to go straight up. We got to go up, and we got to go horizontal. And there's a variety of forces that help us go up 100 miles, but fast enough to go 17,000 miles per hour horizontally. This was our rocket before. Let's pretend it's a javelin. At what angle do you want to throw a javelin so it goes the farthest? Well, the javelin has some interesting characteristics beyond just our ball. It has a nice point at the end, but it also has a shape that changes based on what the angle is. There's going to be more resistance if you throw it this way, less resistance if you throw it this way, maybe a little upward force at an angle. So there's another variable that when you're throwing at an angle, but you're also holding the javelin at an angle, and you get that just right so that you can throw it the farthest distance. Again, it's not exactly the same as a rocket, but there's similar things to consider. There are many factors to consider when a rocket is put into space. Thousands, tens of thousands, maybe even millions of things you have to decide whether I'm going to do this, whether I'm going to do that. Doing this may be the best thing, but then it makes something else not as good. And so if I pull this back a little bit, make this other thing better. It's all part of rocket science. What did we say about what's happening in our orbit? The rocket is constantly falling, constantly falling towards the Earth or whatever object is orbiting around. So we need to be going fast enough that the falling matches the curvature of whatever we are orbiting. So try those activities, and we'll catch you with another video of Mr. Tom and STEM Kids in Space!